So we will be discussing stellar evolutions today, and this front slide, that this image is basically an artist rendition of the stellar evolution of sun. Okay, that is, some sun starts from as a normal star and it expands and expands, finally at the end stage expands to red giant. And after that red giant space itself, it is again expands to become something that beautiful that you are seeing at the right side, which is called a planetary nebula. So it is roughly the artist rendition of the sun's evolution. Okay, now we will be talking about the evolution of stars in general. Okay, and we will be classifying, or we will divide it into two. Okay, so why we are dividing it into two? We are dividing it into two types of stars. One is about sun or similar kind of stars. Okay, what is the just a second. Yeah, okay. So what is the evolution of sun-like stars? That means stars with a mass which is comparable to sun's mass, something, or properly say the stars which has mass less than 8 times the solar mass. Okay, throughout this session we use a term called a solar mass. We already know that it is just to say that how many times of sun's mass it is. Okay, so it is convenient to, instead of saying some 10 to the power 36 kilogram like that, it is always better to compare it with the sun mass and say. Okay, so that is why if the mass of the star is less than 8 solar masses, its life will go in a particular path. And for stars which are more massive than that, that is more than 8 solar mass, the life will be different. So we call it as giant stars. So for the giant stars, the life will be a bit different. So we will explain both separately. So, but the initial stages, something like the formation, is actually almost the same for both kind of stars. Okay, there won't be such difference, but towards the end stages of life, they differ actually. Okay, so the stars are being formed in something called a nebula, or we call it as, more formally we can call them as molecular clouds. They are called the stellar nurseries. And these molecular clouds, something that you see here, this is the pillars of creation. Similarly, Orion Nebula is there. Many kind of nebulas are there from which the stars are being formed. Okay, and what is the speciality about this nebula? Nebula means actually, it is actually a dense cloud of gas. Okay. So gas and dust and everything. So gas in the sense, it will be mostly hydrogen. So the most material, something like the more than 75% is actually, or 70% is actually hydrogen. Then some significant amount of helium will be there. Some remaining other elements also will be there, and from which the next generation of another generation of stars will form. And its mass, the total mass of such a nebula that we are seeing from something like just simple photograph, is of the order of 3 million times the solar masses. Okay, just see, it is not just one solar mass or 100, it is a million times the solar mass. And its size is something light years across. Its size is actually some 1,000 light years across. But even though we say that it is molecular clouds and we see that it is so dense, something like this, but if you go there, you cannot see anything like this. So it is not at all dense when compared with the other things. Okay, so why we are seeing it something like this interesting shape and all? Because we are so far away and we are seeing that 100,000 light years across thing together. That is why we get this feel. It is something like you are looking into the fog. Okay, when the fog is far away, you can see. If you go inside the fog, you cannot see the fog. It is something like that. And an interesting count about this is actually the nebula has some 10 to the power 5, 10 raised to 5 particles per meter cube. So if you take a box of 1 meter size and if you measure the number of particles, it consists of some 10 raised to 5 particles. So it appears to be a big number, but just compare it with the normal air density. So if you consider the air that we breathe, even that itself consists of 10 raised to 25 particles per meter cube. So now just understand how rarer it is, how less dense it is when compared with the air. But even that less dense or rare cloud can make the star. And where does this star form? Inside this molecular cloud. inside this molecular clouds itself, there are some clumps of matter, which is actually some 50 to 500 times more massive than sun. They are called as clumps, and within the clumps, there are some small regions called cores. They are called the embryos of stars. So in that cores, a star starts to form. So star, basically we can say that they are getting birth from the molecular clouds. Now, how does it start? Okay, so for a star to become, we know that we need some material like a gas. Okay, maybe because of temperature it becomes plasma or whatever it is. Anyway, we need something in a spherical shape that has to become a sphere of gas. Then at the core there should be that reaction, that nuclear reaction should happen. This is the basic idea. So we have an idea about stars. We want to make this from here. So now here also it is actually a cloud of gas, but it has some random shape like this. It is not spherical in any way. So to become spherical, so the things become spherical when there is a enough gravity. Okay, so why almost all the planets are spherical in shape? So even though some planets are gaseous, some are solids, some are ice, whatever it is, all of them has spherical shape. So why this spherical shape is so important in all these cases? It is because, so you know that when there is heavy mass, it has gravity. So gravity will act symmetrically inward, or even just assume that suppose a planet formed in this random shape, okay, something like a huge planet, and if it is so massive, then there will be, so this part will get more, so this part of the planet will attract this distant part to the center. So the shape become almost something like this. Now it is actually protruding here. So this will become, so it, due to its own gravity, those objects can become a spherical shape. Okay, so that is why the spherical thing is. But one thing is that it should have enough mass. Okay, if it doesn't have enough mass, then it cannot become a spherical shape. So it need mass, or it need gravity. For gravity, it need mass. So not just the molecular cloud is enough to become a star. So this molecular clouds should come together or accumulate together to become a high massive thing. So that is the initial stage of the formation of a star. Okay. So from the nebula is basically called gas and dust. And what will happen? There is something called a gravitational collapse begins. So some part of this molecular clouds clumps together. So when it comes together, what will happen? So that region's mass is increasing, its density is increasing. When the density is increasing, its gravity will also increase. Now the gravity increases means it can attract more mass around. Okay, more mass that is around it, it can be attracted again. So attracted again. So it can comes together more. So as it gets more and more mass, it gets more and more gravitating, so that it can again get more and more. So it keeps on going on, and it becomes, and there will be, as it goes, its mass is increasing and gravity increasing, it can become a spherical core at the center. Okay, you can see a spherical core at the center, and still more matter is coming, and that matter will form a kind of a disk around that, which is called the accretion disk. Okay, so a core will be formed, and again that again more material will come. This will be rotating as well, and that rotation keeps on moving. Now at a certain time, and there is one more thing, when two objects that are here, okay, so just imagine two things are here, they are attracting each other. If you let it move, it will comes together. So it will come with a certain speed. That means it will collide together. At that time there will be heat. Okay, so when something is compressed or collapsing because of gravity, its temperature will rise. Okay, so it starts to heat. Okay, so it becomes heating. So the heating will start, and when the temperature rises, there will be infrared radiation being emitted. Any heated object can emit infrared, and after that there will be a certain stage called the protostar, the final one. You can see at this stage, okay, the star, that hot core, that gas globe, or that gas, what to say, yeah, that core starts to glow because of temperature, because of the temperature, that because of the gravitational collapse, because the material is coming together. That is why it is glowing. It is not because of any other kind of reactions. Okay, so it starts to glow and it is called a protostar. Okay, so that is the case of a protostar. Now, we can say that it is actually the just before stage of a star. We cannot call it as a star. It is called a protostar. That's it. Now the next stage happens, that is the birth of the star in the next level. Okay, that means there are some problems for being for the formation of star. You know that for the formation of star there should be an energy source. That energy source, as you know, it is hydrogen burning to form helium. Okay, so you know that it is not hydrogen atom anyway, it is hydrogen nucleus. And as we discussed, in the hydrogen nucleus, there is only a positive charge called the protons. Now we want to combine protons together to form, or for protons to form. Even it is through some series of process. Anyway, we have to accumulate for protons to form a helium. But the problem is that the protons are positively charged. If you take two protons and if you try to make it together, they will repel, because like charges repel, as you know. So that repulsion is called the electric repulsion, or more formally we call it as the Coulomb repulsion. So the name is Coulomb repulsion. Okay, so when protons or hydrogen nuclei are positively charged, so they repel each other due to Coulomb force, or we call it as Coulomb force, or we can simply call it as the electrical repulsion. Okay, so because of that electrical repulsion or Coulomb force, we call it as the Coulomb barrier. That means they are not coming together. It is something like if you take two north poles and try to make it together, it is actually difficult. Like that, there is a barrier because of this charge. Okay, so but if this fusion need to be occur, then the proton must overcome this barrier or overcome this repulsion. For that, one thing we have is the temperature. So because it is gravitationally collapsing, its center temperature is so high. So as the temperature gets more and more and more, this protons will be moving so fast, so that sometimes it can almost come colliding, almost comes closer. But the problem is, even then the stars cannot. So this barrier cannot be, for a normal star, cannot be overcome just with the temperature, but along with there is some another interesting thing called a quantum mechanical tunneling. But I'm not going to explain what it is here, but this is one thing where this interesting thing happens called a tunneling. Okay, so that is one thing. So the temperature is not enough to make two protons together. There should be another phenomenon should be happening. That another phenomenon is the quantum mechanical tunneling. So due to that, what will happen? And also with that high temperature, something around 10 million Kelvin, for a sun-like star at the core, the protons can fuse together to make what is called the helium. So the energy generation will start, and the energy generation will happen only at the center. Okay, so yesterday also we mentioned that the energy generation is happening only at the center, not around or throughout the star. So but we haven't said what is the reason for that. The reason for that is simple. So for the fusion to happen, we need a high temperature and pressure. So that high temperature and pressure is available only at the center. As you go outward, the pressure is decreasing, also the temperature is also decreasing. So that enough temperature is only available at the core, and the star is born from that. Because of that high temperature, hydrogen starts to burn. Burn is a common term that is used in astronomy when we discuss about fusion, but the proper name is fusion. But even burning is used, but don't consider it as a normal burning of something like the charcoal burning or some paper burning, but that is a kind of a fancy word that we use, that's all. So here hydrogen is being fused, starts to fuse, and once that hydrogen fusion starts, we can say that the star has born. Okay, so that is the birth of the star. So the birth of star is marked by the fusion of the hydrogen. So whenever the fusion of hydrogen starts, we can say that, yeah, there is a star. But there is a problem. So when it is a star, since it is a hydrogen fusion, a lot of energy is coming out of that. It is something like a huge hydrogen bomb. but the star doesn't explode. Okay, so due to this high energy, there is pressure outward. So it is high temperature, so it is trying to go outward. But at the same time, even though there is an outward pressure because of the nuclear reaction happening at the core, the star doesn't explode. Why? There is an opposite force which is inward acting, that always attractive gravity. So gravity is always attractive, and that attractive gravity is actually pulling the star inward, and this nuclear reaction is pushing the star outwards. Okay, so this pressure, so this is two kind of pressure are there. One pressure is the thermal pressure. Thermal pressure in the sense, when you heat up something, even though if you heat up something inside the pressure cooker, you know that we are actually heating. So the gas, the vapor, everything expands. So it is actually trying to expand, and that increases the pressure. That is the thermal pressure. And along with that, there is another pressure which is not usually heard, that is called a radiation pressure. Because the light is coming, the light itself can exert a pressure on the material, that is called a radiation pressure. So the pressure outward is a combination of radiation pressure and thermal pressure. Okay, so this two pressure is there, and this is actually trying to disperse the star actually. But at the same time, this gravity is actually pulling inwards, and they are in a balance. Okay, so this gravity and this pressure are in a balance in the sense they are actually cancelling each other. Okay, so that is why the star is being in a stable form like a sphere. Otherwise, suppose imagine that if the radiation, the inside pressure is more, the star will disperse or star will expand. And imagine that there is no outward energy, then the gravity will increase, then it will collapse. Okay, so it should be in a balance, and that particular balance or equilibrium is called hydrostatic equilibrium. Okay, so when it is achieved, the outward radiation pressure from the fusion balances the inward gravitational pull. When they are in balance, it will stay like that. So that is the stability of the star. But when there is something just not here, the in the coming slide we will say that sometimes the star is expanding, the star is contracting, like that. So whenever we are mentioning that, if the star is contracting, just understand that the gravity is more. Okay, when the star is expanding, that means the inside pressure is more. Okay, once the pressure is more, it will expand. Okay, now there is another interesting thing. They are actually in a self-balance star. Okay, so it is something like a balanced system. So that balance is something like this. We can explain. So suppose the star is stable like this. So for some reason, just imagine that the nuclear reaction has increased. Okay, so there is a high nuclear reaction. The nuclear reaction rate is increased. It becomes faster. Now what will happen? The star will expand because now the pressure is more. So when the pressure is more, the star will expand. So at that expansion, what will happen? During that expansion, the center pressure will decrease. Okay, and the center temperature will decrease. So at the same time, again the reaction rate will decrease. So if the reaction rates increases, the star will expand, and due to the expansion, again the reaction rate will come to back to normal. So this is in a balance actually. So that is one advantage of this system. So it is in a hydrostatic equilibrium. So that is why sometimes the star may expand due to the high pressure, then it will go back to the older size. So that kind of oscillations, that means that expanding and contracting may happen for star, but even though in that case, that is in equilibrium, or it is balanced there. Okay, now there are some mass criteria for the birth of star and for the size of a star. One is called the Jeans mass. Okay, so the Jeans mass means, so it is a minimum mass required for a gas cloud to collapse under its own gravity and form a protostar. So it is, so for a star to become a protostar, okay, it need a certain amount of mass. Okay, so and it is not a certain mass. We cannot say that this much mass is needed for that. It depends on the size of the star being formed and all. Okay, so it is based on some equations we can calculate the Jeans mass. So that is why we are not saying that this certain amount of mass is needed or anything like that. Okay, so if a clouds of mass is less than the Jeans mass, it will not collapse. Instead, it will disperse due to thermal pressure. Okay, so that it will try to come together. If it cannot achieve the Jeans mass, there won't be the formation of protostar. So the gas cloud, to become a protostar, it should satisfy, or it should have enough mass that is defined by the Jeans mass. Okay, now if the gas cloud has more mass than the Jeans mass, then okay, now the protostar is formed. Now there is another thing. Even if the protostar is formed, the star has to become the next level star. Okay, that means the hydrogen burning should happen. And the star in which the hydrogen burning is happening is called a main sequence star. Okay, I will explain later why it is called the main sequence and all. Anyway, it is called the main sequence star, where the hydrogen is being burned. Okay, so the star from the protostar, it is going into the next phase, that is main sequence. Okay, so now what is the hydrogen burning limit? So for a protostar to sustain or to happen the hydrogen fusion in its core, it should need a minimum mass, and that minimum mass is 0.08 times the solar mass. This symbol is This is an astronomy symbol. This means sun. Okay, because it looks like solar system, and this is Earth. Okay, so M, this means mass of Earth. M, this means mass of sun. So it's another symbol. Just okay. Now, or simply we can say that 80 times the mass of Jupiter. If something has 80 times, a protostar has more mass more than 80 times the Jupiter, then only it can start the hydrogen fusion, and that is called the hydrogen burning limit. Below this limit, so just assume that a protostar is formed because it has more mass than the Jeans mass. Then that protostar, if it couldn't achieve or if it couldn't acquire more mass than this 80 times the Jupiter mass, then it cannot burn the hydrogen. Okay, so that it won't become a star, or it becomes a failed star, or which is called the brown dwarf. Okay, so that are the brown dwarf. They are not stars at all. Okay, so we can simply call them the failed stars. And now there is another limit called the Eddington limit is there. So Eddington limit is the upper limit of the star. So stars can be formed with the different masses, something like the 0.08 times the solar mass, 1 solar mass, 10 solar mass, 20 solar mass. But there is an upper limit for the total mass of a star, or the maximum a mass, how maximum a star can be, massive can be. That is also defined by the Eddington limit. Okay, so its value is estimated to be 100 to 150 solar mass. So there won't be any star which is more massive than 150 solar masses. Okay, if a star gets that much amount of more than that 150 solar mass, then what will happen? Because of its own radiation pressure, the star will lose its mass and explode as a supernova. Maybe it lost mass, or it suddenly explode as a supernova. It cannot stay stably like that. So that is why it is called a Eddington limit. So these are some of the limits that we see in the during the formation of star. Now there are some other limits as well, like the Chandrasekhar limit that we will discuss soon. Okay, now this is called the main sequence star. So what is the speciality of a main sequence star? Yeah, it is the first. It is a newborn baby. We can say that. Okay, it is one of the important stage of the star. So when the hydrogen burning, so initial burning that is happening at the star is hydrogen is being converted into helium. And this stage of the star is the longest lifetime, or in the there are different phases for a star. Protostar phase will be there, main sequence will be there, red giant will be there, then maybe next level of red giant will be there. So during all this phase, the longest life is actually, we can say that we may spend most of the time by studying in the school. So that is actually a long time. Okay, something like that. So this is the longest and most stable phase of a star's life, and where the hydrogen is being converted into helium through nuclear fission. And it is something similar to that of sun. The hydrogen is happening at the hydrogen fusion is happening at the core. Around that there is a radiative zone. Just outside that there is a convective zone like the sun. So that is what is happening there. I'm not going to explain all these things here because we already learned the sun very well. Okay, so the same thing. Sun is a main sequence star. So if you want to have an example for the main sequence star, the best one is the Sun, because the nearest one and the easiest. So now you can see what is the lifetime of stars in the terms of main sequence, how much they spend as a main sequence. Okay, you can see that if the mass of the star is 40 times the solar mass, here it is ms, means we are saying it as 40 times the solar sun's mass, then it will last only 1 million years. So that is the life expectancy in the main sequence. Okay, it will spend 1 million years in main sequence. And now you can see if it is 16, then that is the mass is reducing 10 million, and when it becomes 1.7, 2.7 billion, 1.1, 9 billion, and if it is 0.8, that is 14 billion, and in between there is our 1 billion, that is sun, around 10 billion years. And if it is 0.4 times the solar mass, it can last up to 200 billion years. So just see that interesting thing. When it is more, when the star is massive, its life expectancy is small, okay, or it cannot last for a long time. And when it is less massive, it can last for a long time. Why is it so? That is an interesting question. So consider two stars. One is a big star and another is a small star. And the big star means more massive, something like a 40 times the sun's mass. And suppose this is sun. Okay, so this star has one solar mass, or it is simply sun, and this star has 2 times the mass of it. We can call it as A and B. So A has 40 times mass of B. Okay, now it has 40 times mass of sun, means it has that much amount of gravity as well. So it is so very high gravity. So that means the pressure towards its center is so high. Not just the pressure, you can see that along with the pressure, as the pressure increases at the core, even the surface, you can see this is the temperature. So the core temperature will be so large. So since the core temperature is so high, the hydrogen burning will be faster. Okay, if the temperature is less, something like a 10 million for the case of sun and all, the hydrogen burning rate will be less. So when it is a massive star, due to gravity, the core temperature will be high, so that there will be higher rate of fusion. So the fuel gets burned so fast. So that is why its lifetime is not is less when compared with a less massive star. For a less massive star, there is not that much high temperature at the core, so the fusion rate will be so slow. It will burn fuel so slowly, so that's why it can last up to some 200 billion years or maybe 10 billion years like sun. Okay, so that is the reason for that. Now the next stage, so this is the main sequence stage. So I will explain why it is called the main sequence later. Okay, before that, let's go, and it is going to the next stage. That means we cannot have enough. And one more thing, as we mentioned, the I already mentioned, I think. So the reaction will happen only at the core initially. So the reaction is happening here. So what will happen? Eventually, all the hydrogen at the core, even though this is completely, the remaining part is also hydrogen. Okay, this envelope is actually hydrogen, but the reaction is happening only at the core. And at that core, all the hydrogen is being converted into helium. And finally, at some stage, there won't be enough hydrogen. Okay, so we will run out of hydrogen at the core, or hydrogen will be depleted at the core. So what will happen? It completely becomes helium. Okay, just leave these things. Okay, so it completely becomes helium. And now what is the problem? So when it is completely become helium, there is no energy generation. So hydrogen is complete. We are out of fuel. Simply, we are out of fuel. So out of fuel means there is no energy outward. So there is no energy outward means the gravity is dominating. So when the gravity dominates, the problem is that the star will compress. So when the star compress, another thing will happen. So when the star compress, again the temperature will increase. So due to that increased temperature, initially the shell just outside the helium, so it is the this core is actually helium, just outside the helium, the hydrogen burning will happen. Okay, so here the hydrogen burning is happening, just inside it is helium. And after some time, okay, now at this stage there are some problems. So now the hydrogen burning is happening just outside the shell. Okay, so because here it is happening at a much bigger volume, there is more energy is coming out of the star. So the burning rate, not just the rate, the amount of burning will be more, so that the star emits more light. That means more energy. So that now it dominates the gravity. It dominates the gravity means the star starts to expand. So the star will get expand and its size becomes so large so that the problem, it's not a problem, it becomes a giant star. So it expands means its size will increase. So as it expands, the surface will get cooler and cooler because it is farther away from the star. So each portion of the surface will get less light or less energy. That means the surface becomes cooler. So surface becomes cooler means the cooler means it becomes reddish in color. Hotter means it becomes bluish in color. Okay, because high energy is for blue and less energy is for red. So it becomes a red in color, and already it is a giant star and it is low in, it is surface, it's so cool. So what will happen? It looks like a red giant star. It's not just look like it is a red giant star. Okay, so that is called the red giant phase of a star. Okay, so now just after that, even just after that stage, there is one more thing will happen. So this helium core is sitting right like this. Okay, so all the burning is happening here, and it will expand the star in this direction and becomes a red giant. But the helium core, there is no energy at the center. So helium core can further shrink. Okay, it can become a bit more smaller, and again some energy generation. The helium will starts to burn. So again it will compress. So when it compress, again the temperature of the helium will increase. So the problem why it is not happening suddenly when at the initial stage, why can't we burn helium directly? The problem is that for the helium to burn or to helium to become another elements like a carbon or oxygen, it needs some 100 million Kelvin. So this will happen only when the core compresses or contracts, and it core temperature becomes when it becomes something 100 million Kelvin. So the helium starts burning. That burning process is called okay. So that it happens like a sudden explosive event, and it is called the helium flash of the star. So helium flash means it the star is starts to burn helium at the center. So now see those layers. The inside layer is actually helium burning cell. So actually, if I draw properly, this is just for the reference only. If it is proper, actually the helium burning will happen at this center, and just outside that there will be simple helium, nothing is happening to that. Then just outside hydrogen burning, that is hydrogen being converted into helium. Then just outside that hydrogen. So this is the status of that star. It will starts to look like different layers. Something like if you cut an egg or something like a nut or something, you can see that different types of layers are there, and each of the layer different processes are also going. Okay, now let's go back. Okay, now but in the case of high mass stars, this won't happen like an explosion. It will smoothly go to the next stage. Okay, that means hydrogen will burn, then the after that eventually normally it will start to burn the helium. There is no need to wait for the helium flash or anything. So that is the next stage of the star. Now, when the star, even at this stage as well, the star looks like a giant itself. And at that stage, it's so big in the sense you can see its age, when the sun becomes at an age of 12 billion years, this will be the approximate size of the Earth. No, sorry, sun. You can see the sun becomes near the Earth's orbit. Okay. Now, these are all some other comparison of red giants and some red super giants. Okay, when the high mass stars become red giant, it is called the red super giants. So these are all super giants or hyper giants, which is compared with the size of the sun. Sun is here, you can see. Okay, so this is about the red giant phase. Now let us go to the next level. What will happen? So if you remember here, the helium is being converted into carbon and oxygen. Okay, carbon and oxygen. So helium is converting into carbon and oxygen. So finally what will happen? The center will consist of carbon and oxygen. Next layer, there will be another small outer layer will be there. In that, helium burning will happen, and just outside layer, helium will be there. Next layer, there will be hydrogen. Next, hydrogen burning. Then the next layer, there will be normal hydrogen. So it becomes something like an onion. Okay, it's not properly an onion, but when you see, you can see that. Okay, so helium will be exhausted in its core. Okay, so it is out of helium, leaving a core made mostly of carbon and oxygen. Okay, then helium shell is burning. Helium fusion occurs in a shell around the core. You can see helium fusion is happening here. Then just outside there is a helium core. Then just outside the hydrogen shell. Then just outside that simple hydrogen is there. Okay, so this is a series of process or series of different kind of processes are happening there. Okay, in that stage, because of the high energy, because all these layers are burning, there will be high solar wind will be there. Solar wind or stellar wind will be there, and due to that stellar wind, okay, I will come back to here later. Okay, this outer layers of the star, okay, especially other than the core. So we had a core here, that is the carbon and oxygen core, and the remaining outside layers like the helium burning, hydrogen burning, these shell will be expanded to the space. Okay, and that will be expanded to form a structure like this called a planetary nebula. Okay, and but at the same time, even though the outer layers expands, the core is actually remaining. What was the core? The carbon or carbon and oxygen core. And that carbon and oxygen core will remain like that because there is nothing is happening there. There is no fusion is happening there. And not that this is for the case of stars which has mass less than 8 solar mass. Okay. From the giant phase, we are saying this is happening for this planetary nebula stage is happening for sun-like stars. Okay. It is not for heavy stars or massive stars. And now that core remains there as something called a white dwarf. Okay, so that will be the final stage of the star or final stage of that core. Okay, and core cooling and collapse, the remaining core composed of hydrogen and helium, hydrogen and oxygen collapses into white dwarf. Now the white dwarf, usually for normal solar masses, the white dwarf mass will be less than the 1.4 solar masses or less than the Chandrasekhar limit. So what is this Chandrasekhar limit says? So suppose you have a white dwarf star and it can stay as a white dwarf star for its lifetime only if its mass is less than the Chandrasekhar limit or 1.4 times the solar mass. If its mass is more than the Chandrasekhar limit, it cannot stay like that. It will further contract and become something else, something like the neutron star we will discuss later. Okay, and there is one more interesting thing, why this star is not collapsing, because there is no energy is coming outward. Okay, no energy in the sense no fusion is happening, still some temperature will be there, but it is not, why it is not the why the white dwarf is staying like that. Okay, why the gravity cannot compress it further even though it has some mass of something around the mass of sun for some other stars. Okay, why that is happening? Because there is another interesting kind of pressure called degeneracy pressure. Okay, so what is this degeneracy pressure? It is some kind of, so we know that there are electrons inside the star. Okay, electrons are separately there. So electrons has a special property that you cannot place many electrons together. It is not because of the charge. Already because of charge they may repel, but other than that, this particles, they are called fermions, has a property that they cannot sit together or they cannot come closer for us after a certain limit. Okay, so they will exert a pressure and it is called a degeneracy pressure. This is purely some kind of something related to a branch of physics called quantum mechanics and all. You just leave it. Anyway, that pressure is degeneracy pressure. Just keep this word in mind, nothing else. Okay, its explanation is a bit difficult for you. Okay, so because of that, it exists like that. And now if its mass is more than that, something else will happen that we will discuss later. and the temperature, it is extremely hot initially and but small. You can see it is so massive and high in temperature, but it is small, something about the size of Earth. So almost the size of mass of the sun being concentrated into a size of Earth. It is almost the case of a neutron star, so that its density is so high, even if you take a teaspoonful of white dwarf material, okay, it will weigh almost 9,000 kilograms. And now here what you are seeing here, this bright one is actually the star Sirius. Okay, that is the brightest star in the night sky, and we call it as Sirius A. And near to that, you can see another tiny star, which is called a Sirius B. Okay, and that is a white dwarf actually. So Sirius B is a white dwarf star. Okay, and in that white dwarf, there is no fusion is happening, as you know. And after some trillions of years, it is supposed to say that it will lose all this temperature it had, and it becomes something called a black dwarf. But we haven't observed any black dwarf yet. Can you say why we haven't observed any black dwarf yet? Why we haven't seen any black dwarf at all? Yeah, the reason is that you can see here, what is the time taken? Suppose the time taken is trillions of years. The universe is just only billions of years old. So we cannot see something that is going to happen after trillions of years within this billions of years. That is why we might haven't observed any black dwarfs at all. Okay. Now, what about the evolution of high mass stars? Okay. So in the case of high mass stars, so they are so massive so that there is some other advantage. So the carbon, so we said that there is carbon at the center for sun-like star. But in the case of high mass star, again the pressure and temperature will increase so that the carbon and oxygen can fuse or burn to form the next level. Then again it can again the next, so a series of process will happen, and finally the structure of star becomes something like this. You can see iron core. So what happened, and just outside that silicon and sulfur is fusing, then magnesium and neon. So what happens is actually an interesting thing, something like, just imagine, so this is the initial core, so this was the hydrogen core. Okay, hydrogen was burning to helium. Just outside that we had helium. Now what will happen? After a certain time, there is no hydrogen remaining. So the outside layer will start to burn hydrogen. The inside helium will be there. And finally, the helium will start to burn. And that helium will become carbon. And then that carbon will burn. And a series of processes will happen. And in that series of process, there is a problem. You can see that this is the mass number. That means it starts from the hydrogen. This is hydrogen, then helium, like that. But when you go, this is something called a binding energy. It actually a measure of how stable a nucleus is. Okay, binding energy plus per nucleon. So you can see here who is at the peak, that is iron. Okay, so up to here, okay, these are all the lower material or lighter elements. We can go here. But further, if the iron is came at the center, the iron cannot fuse further. But up to that, there will be series of fusion will happen. The hydrogen become helium, helium becomes carbon and oxygen, then carbon and oxygen becomes magnesium, becomes neon, neon to silicon, silicon to sulfur, sulfur to iron. But at iron, it will stop. So once it is reached the iron, means there is no further fusion will happens at the center. Okay, now what is the problem? So the problem is that a supernova expansion. So when the iron core reaches a mass, okay, which is greater than the Chandrasekhar limit. So iron core is becoming bigger and bigger and bigger, but finally when its mass becomes more than the Chandrasekhar limit, but it happens only for massive stars where the mass of the star is more than 8 solar mass. Okay, for giant stars only, this mass of the iron core becomes more than the Chandrasekhar limit. And what will happen? The core collapses violently, and this triggers a supernova. So initially it happens as a collapse, and because of that collapse, there will be a supernova explosion, which is one of the most energetic events in the universe. Okay. Now, after the core will collapse, and because of its shock waves and all, the outer layer will be ejected at high velocities. So the outer layer will be ejected to outside, and there will be lot of emission of neutrons, neutrinos and all. And during this, another spectacular thing is happening, that is heavy elements will be synthesized. So what do you mean by that? So you can see that inside a star, or you can imagine that after the Big Bang, there were only hydrogen and helium, some lithium, that's all. There is no other material was there in the universe. Now, inside a star, what will happen? We cooked more helium, then oxygen, carbon, magnesium, neon, silicon, sulfur, up to iron. Almost all the elements up to iron being formed inside the star, inside a giant star, okay, or inside a red giant. It is okay. But what about the other element beyond iron? Okay, there is calcium, uranium, thorium, maybe that kind of many other elements are remaining to be formed in the periodic table. So this is not formed here. Okay, all these are formed during the explosion of a star or during a supernova. The intense energy of the supernova can fuse even heavier elements beyond iron. Okay, so that is how we have all the elements, and what you are seeing here is called a Crab Nebula. Okay, again it is called a cloud, molecular cloud, which is actually the remnant of a supernova. So after the supernova, I said that it will eject out materials and all these elements will be formed, and it together is seen like this, like the nebula, and that is called the supernova remnant, or we can the name of that nebula is Crab Nebula. Okay, there are many as well. And there is some interesting facts about supernova. I said that already. It is a one of the energetic phenomena in the universe, and and its energy generated is 10 raised to 44 joules, and it happens within a week. The maximum lifetime of a supernova is actually something around weeks to months. That's all. Within a week or to couple of weeks, it will emit almost 10 raised to 44 joule. And that 10 raised to 44 joule, okay, just a number, but now imagine that it is actually a billion times the total energy output of the sun over its entire 10 billion lifetime. Okay, so sun will emit some energy in its entire 10 billion lifetime. So the supernova will emit billion times of that energy within weeks. Okay, so that is the supernova. And a supernova will outshine an entire galaxy for a brief period. Okay, and it is billion times brighter than the sun. And I am lucky enough to watch a supernova that happened in I don't remember, maybe around some 2015 or something. Something happened in a galaxy called the Cigar Galaxy. Okay, I was lucky enough to watch it through the telescope. So you might be thinking that it looks like something, an explosion, something like a firework, but exactly what I have seen. So the galaxy itself, when you see through a telescope, even through big telescopes, if you observe through the telescope, you will see it as just a cloud. You cannot see individual stars actually. It will be something like a faint cloud. But okay, that is the even though there are billions of stars, you will see it just like a cloud. But when there is a supernova, that particular star, okay, that exploded star will look like a bright dot like this. Okay, so this is actually the photograph. This is not the what you see, but you can see here a bright point. That bright point is actually the supernova. So that supernova becomes more brighter even than any stars in that galaxy. And now another thing, the temperature is actually 10 billion Kelvin. So sun temperature, you know that 15 million only. And the material will be ejected at a high speed of some 10,000 to 30,000 kilometers per second. So maybe comparable to some 10% speed of light. You can see this is if there is one more zero, it is actually the speed of light. It is actually the 10% speed of light it is moving. That is the speed of the supernova ejected material. But at the case of sun, the solar wind is just 400 to 800 kilometers per second. So why I am comparing it to the sun? So just to see how bright, how energetic that event. Okay. So now what will happen to that iron core? If you remember that there was an iron core at the center that is collapsed. Okay. So that collapsed star or collapsed iron core, so that iron core will consist of protons and electrons and neutrons, basically the particles inside the atom. So it consists of protons, electrons and neutrons. Now what will happen? These protons and electrons come together and form something called neutrons. So finally that iron core become completely full of neutrons, and that is called a neutron star. So this only happens when if the core mass is between 1.4 and 3 solar masses. Okay, so 1.4 to 3 solar masses, the iron core, then it will stay like a neutron star. Okay, and neutron star, just imagine its mass is something around 1.4 to 3 times the solar mass, and its size is incredibly small, that is 10 to 20 kilometer in radius. It is actually the size of a small city, not a big city. It's actually the size of a small city. You can see that is the size of a neutron star, and the entire mass of maybe 1.5 times or 2 times the mass of sun is compressed into that small area. So you can imagine how dense it is. So already it is dense and high in gravity. Okay, and it is highly magnetic in nature. Strong magnetic nature is there, and it can emit beams of radiation. So this beams of radiation has an interesting feature, and when this is rotates, this is actually spins itself. So when it spins, this light beams will be pointing in certain direction. So when it rotates, actually this beams also moves. Okay, something like a lighthouse. So from Earth it can be observed like some light comes and go and comes and go. So it looks like a what is called a lighthouse, and we can call it as a pulsar. Okay, so that is about the neutron star. Now we said that the neutron star stays like a neutron star only if the mass is between 1.4 times and 3 solar mass. So what if it is more than 3 solar mass? Then again, so if it is more than 3 solar mass, then again it can collapse once again, and that collapse will lead it to something called, it is called the black hole. Okay, where the gravity is so strong that not even light can escape. Okay, so that is final stage of a star. So final stage in the sense, we cannot say that it is the final stage. I will summarize it later, then it will be clear. So either the high mass star become a neutron star. If it is even massive, then it becomes a black hole. So the death or the end stage of a massive star is either a neutron star or a black hole. Okay. So that is about it. Now we can brief this in this single picture. That is, you can see the top line is for the low mass or medium mass star, including sun. So the main sequence, then red giant, then planetary nebula, and white dwarf. And here you can see that it is high mass star, red supergiant, supernova. Either it becomes a neutron star if it is high mass star. If it is very high mass star, it becomes a black hole. So that is the final stages or different stages of a star. So it all depends on what was the initial mass. Okay, how it started, or how much mass it had at the beginning. So that defines its life. Okay, so even though we say that the high mass stars lives only millions of years, but all the elements that you are seeing in your periodic table or in your body or whatever that supports life is actually almost all of them are cooked inside the high mass stars. Okay, so we have to say thanks to those high mass stars, those actually exploded back then and from some billions of years ago, and from the remnants of that, actually the next generation star, the sun, being formed. So that is why sun consists of all these elements, and the disk around the sun also consists of those elements, and that is why earth consists of all those elements. That is why we evolved like this. Okay, so we have to say thanks to those exploding stars. Okay, now let's see another thing that is related to stars, but anyway it is not there in your syllabus. It is not particularly written in your syllabus, but I will explain it. So this is actually the brief case different. So for low mass stars means you can red giant, horizontal branch, asymptotic branch, just leave these names. Okay, these are all related to what I am going to tell in the next slide. Okay, so here it is just the summary of the evolution of low mass, and this is the summary of the low mass star. Okay, this is just for reference. I'm not going to explain it again, but you can, if you want to have a comprehensive uh, understanding, you can, or if you want to know it in a single slide, you can read it. Okay, that's why I include that. That's all. Now there is and you have seen some names like horizontal branch, asymptotic branch, main sequence, and all these things. Okay, all these names are actually came from something called a famous diagram in stellar physics or stellar astrophysics, or stellar astrophysics means the physics, astrophysics related to stars. So that is called Hertzsprung and Russell. So Hertzsprung and Russell are two persons. They independently found the idea of this diagram. So if you want to draw this diagram, just leave this rounds and this blue, yellow, all these circles. First of all, we draw something like this, two axes. Along this axis, if you go to the right, the temperature is decreasing. So you have to note it carefully. Usually in every figure like this, when you go to the right, the temperature or whatever quantity, it is increasing. But in this case, it is decreasing. Now here it is luminosity, that means the energy output. That energy output is going upward. Okay. Now what they did is that, so this is luminosity and temperature. Now scientists observe the star and they measure the luminosity and they measure the temperature. So they got the temperature and luminosity. Suppose it has some 10,000 Kelvin and 10 to the power 2 luminosity. 10 to the power 2 means 10 to the, that is 100 times the sun's luminosity. Then we have to draw that star somewhere here. Okay. And also we can denote its size by the circle, relative size. Okay, almost, just size is not that necessary there. Anyway, we can put it. Then I observe another star, and that star's temperature is around some 30,000 Kelvin and its energy output is 10 raised to 6. Then I will draw it here. Okay, so based on the temperature and luminosity, every star has a position in this diagram. Okay, so what they did, they studied a number of stars and they put each of them, they found, they tried to arrange it in this diagram. So finally what happened? So one thing initially they noticed, almost all the stars or the majority of stars, this is not a realistic case, you can check for the realistic pictures in Google. So you can see that almost all the stars come in this a band, okay, a sequence along this. Okay, they can see something like this. So, and when they observed, they could understand two things. One is actually this is highly populated. So why it is highly populated? So from that, so there is another interesting thing, that how people know that the main sequence is the most long phase of a star. So one thing they know is from the physics. So from the physics, they can calculate how long it can last. That is actually we calculated yesterday. How long with the nuclear reaction it can last, whether it is billion or million years, something like that. That is one thing. Also, they see something that almost all the stars belongs to this phase. Means that out of the total population of stars, this should be where the stars are spending most of its time. So that is why it is highly populated. Okay, so that is why you can see that it is highly populated in this region. So now it is highly populated here and this region, and then when they analyze, they could understand another thing, that is it is mostly in all of them are actually burning hydrogen as well. And that is why this is a sequence that's found in the HR diagram. It is called HR diagram. So, and that is the main one. So that is why they named it as the main sequence. So that is why earlier when I mentioned about the hydrogen burning stars, main sequence, main sequence, main sequence. Okay. Now they found some other clusters there. So the red giant will come here. Okay. So the red giant will come here. Why? Because its temperature is so less, but still its energy is more. So that is why it comes here. Now, what about the red supergiants? They even have low temperature but high energy. That is why it comes here. Now blue giants are there. They are giant stars. So what is the blue giants? Yeah, they are high in temperature, high in luminosity. Now there is some other star called a white dwarf that we are already mentioned. White dwarf are high in temperature, but the problem is that the energy output is so low. Okay, so it comes here. So we can categorize each of the stars in different branches of this. Okay, so that is about the. So the sun will come somewhere over here. Almost this is the position of sun. It comes somewhere over there. Okay, so that is the yeah, that is a HR diagram. So HR diagram is not just to classify the stars. Also, from this actually we can explain the lifetime of stars. Okay, so here you can see that. Just leave that. We will come to that. So as we explained earlier, so initially the sun is here. Then what will happen? The sun will become a red giant. So it becomes a red giant means it will expand. It will increase its size. It will increase its energy output, and its temperature is becoming less. So it will go in this track. Okay, it will come here to a red giant. Then finally it will come one more down. Then it will go something like the white dwarf. So it is actually we can draw a path. Okay, the life cycle of a star can be drawn like a path inside this. I'll give you an example. You can hear. So this is the case of the sun. Sun will go something like shell burning hydrogen, core helium. Okay, helium will start to ignite. That is the helium flash. Then again, for some times the temperature will increase. Then core helium burning, and that is why this branch is called a horizontal branch. Then this branch is called the asymptotic branch. So these are all from the shapes and all. Then fusion yields, and finally it comes here. That is the what is called the that nebula. That is the white dwarf. So life cycle of all types of stars can be explained using this HR diagram. So that is another importance of this HR diagram. So anyway, it is not there in your syllabus, but I just explained. That is because we are actually explaining these names and all. Okay. Okay, now that's about it. Now I will take some questions from the chat, and we will start the direct discussions. Okay. What just happened? Which gas in majority? So wherever you look, as other than the planets, almost everywhere in the universe, it is the majority is actually hydrogen. Even in the case of nebula, the majority is hydrogen. So there is no need to put further questions in the chat. I will take the question that is existing there. Then I will come for the discussion. Okay. Okay. What is the difference between a molecular cloud and a nebula? Okay, they are actually almost similar. Both are actually molecular clouds. Okay, so there is not much difference is there. But nebula, the problem is that nebula can be even the remnant. Something like a planetary nebula is also a nebula. That's it. Is there any star exceeding Eddington? No, there is no star exceeding the Eddington limit. That is why it is called the Eddington mass. That is a limit. Yes, sir. But for surface cooling, red giant star, isn't the outlier hotter than the inner one's chromosphere? Yeah, okay. So even in the case of red giants, the problem is that what we are even if there is corona and other chromosphere which is at high temperature, what we are observing is only the photosphere. Okay, so whenever we are saying the temperature of the surface of the star, we are mentioning the temperature of the photosphere. So there is no such problem. Under slight birth of star, does the increasing and decreasing of a star cause it to become a Cepheid? Yeah, that is exactly correct. Why does the rotation accelerate during the so why the rotation accelerate during the disk formation? So it is something like when suppose there is something is rotating. Okay, it is not due to the disk formation. So when something is rotating, as it compresses, it speed will increase. So it is something like, if you see the ice skaters, when they do some rotation and all, they do some dancing kind of thing. So when they rotates, I don't remember exactly what that thing is. If their arms and legs are spread, okay, then it will be in a they will make a certain speed, and after that, if they make some, when they contract their legs and arms, it will move faster. So that is about the okay, just a second. Yeah, that is about the so whenever something is rotating, if it is contracts, its speed will increase. So that is something called the conservation of angular momentum. Okay, now we will ask, we can have the discussion. So there is no hand rise. Wow. Yeah, we got one. Sri Mahitraj. Okay, you can ask.
Good evening, sir.
Good evening.
Can you explain about the mass criteria?
Okay, so the first mass criteria, first thing that we explained is that, yeah, one is Jeans mass. So Jeans mass is the minimum mass that is required for a cloud to become a molecular cloud to become a protostar. Okay, then if a protostar want to become a main sequence star, it should have a minimum amount of mass that is called the hydrogen burning limit. Okay, it doesn't have a special name, but we can name it as hydrogen burning limit. Now there is Eddington limit. That Eddington limit means that is the maximum mass a star can have. Now we mentioned another star at the final stage of star, that is called the Chandrasekhar limit. So the Chandrasekhar limit means a white dwarf star can stay as a white dwarf only if its mass is less than the white dwarf star. So the stability of the white dwarf star or the white dwarf star will be stable only if its mass is less than the Chandrasekhar limit. Okay, so that is the Chandrasekhar limit or the next limit. Okay. Anushka. Okay. Yeah, Anushka, you can ask.
So can you explain bipolar outflow?
That happens for a neutron star. Bipolar means simple. It is outflow of energy. That is, was that? Just a second. That is the case of energy. So simply, I'm not talking about the particular case. Particular case, I will discuss about the neutron star. Anyway, from that word, what you can add. Bipolar means two polarity. Okay, so when you see a planet, it has two poles. Okay, or when you take a sun or star, it has two poles. So bipolar means both the poles. Bipolar, what you asked, I forgot. So bipolar outflow, I think. Yeah, bipolar outflow means there is outflow of something through the both poles. That is the meaning of bipolar outflow. And here we mentioned it's in the case of what is called the what's yeah. Here we explained it is in the case of neutron star. That means at the both end we can have it is not outflow, it is actually bipolar radiation will be there, and bipolar outflow means there is outflow of material through both the poles. Okay, so that is its meaning. Yeah, any more questions? See any more questions there? And one more thing regarding, yeah, nothing else actually. So yeah, that's it. So I hope there is no other questions. If you have any, I will wait for some 5 more minutes till 8:45. You can raise your hand. If you don't have any questions, and I think then you may leave, no problem. And once again, before leaving, all the best for your exams as well. Okay, write it well, and you can go through these slides. So slide consists of a lot of information, and there will be questions from the slides and the class in general. So Bhargav Deshmukh, you can ask.
Sir, how are the galaxies formed?
Okay, galaxy formation is actually it is basically again by the it has something to do with the black holes, so that is something that hold it, so the stars can come together and form it, something like that. I don't exactly remember the galaxy formation actually. So but anyway, for that actually, one thing that holds a galaxy is the central black hole, and there is some more missing mass. Some more mass is actually needed to explain the existence of a galaxy, and that is basically we are believing that is from the what is called the dark matter actually. Rajani Vishakarma. Okay,
Yes.
yeah.
Good evening, sir. I'm
Yeah, good evening.
Tushar. Sir, actually, I had a doubt in horizontal bend. What is
Yeah.
it?
So horizontal branch and asymptotic branch, you can just understand it's something like when you talk about the stellar evolution, or the that the one star becomes the other, or the main sequence becomes red giant becomes something else. So during that movement, okay, we can trace its path along the HR diagram. Okay, so it starts from here, then there, then something like that we can actually explain. So that explanation, or when you explain it like that, some of the portions of those track, okay, we can track the path of a star through the HR diagram, and certain paths are named at horizontal branch. So horizontal branch basically means the helium burning phase. Okay, then asymptotic branch is there. So these are all the names of different branch that we are seeing in the what is called the HR diagram. Okay, it is HR diagram is not there in your syllabus. That is why I haven't explained it more, because it will take some time. We have to take each of the star and how it moves one by one, we have to consider. Okay, now Levin. Yeah, oh, Levin, I couldn't see you. Where is, can you raise your hand once again? Yeah, thank you. Yeah, Levin, yes.
Good evening, sir.
Yeah, good evening.
So I have two questions.
Yeah.
Do neutron stars cool down like white dwarfs do?
I don't know exactly. I think I haven't read anything like that. It cools down or anything. Yes. I don't know exactly the right answer for that, but anyway, I haven't read anything like that, because of the high energy and high magnetic field. It may cool down, but it should cool down anyway. The energy will lose, but there is no particular name or anything about that. I haven't read.
Yes, and this black dwarfs, neutron stars, and black holes, can these be depicted in the HR diagram as well?
Black holes and
The
neutron
neutron
star.
stars, black dwarfs.
Yes. But black holes for sure we cannot, because it should have a certain amount of luminosity or temperature, because we cannot measure its luminosity because there is nothing is coming out of it. So black hole can be
Then zero luminosity.
huh?
Can we not put it in zero luminosity then?
That may be possible, but we cannot say that it's in that. Okay. So anything, even a light bulb can be placed there, no problem. But whether it is meaningful or not, that is the question. Neutron stars also similarly haven't seen anywhere that is putting into the what is called the this thing in the HR diagram.
Yes, thank you.
Okay. Yeah, Anushka. Yes.
Sir, what happens to a Cepheid after there's white dwarfs formed for other stars? So does like a Cepheid also go through the same process?
Every star will go through Cepheid. Even the Cepheid is also a type of star, nothing else. Okay. So
Yeah, but it's constantly like increasing in its size and decreasing, and like the temperature changes.
yes, but anyway, eventually that pulsation may happen even for other stars as well, even though it is not Cepheid. Many stars go through this at some phase, may cause some this variation and all, but anyway, eventually if it is a star, this should end its life more or less similar way.
Okay, thank you.
Yeah. Dhwani Bhatt. Yes, Dhwani Bhatt, you can ask.
Sir, I wanted to ask your opinion on dark energy and dark matter.
Okay. I will give you the opinion about dark matter. Dark energy, tomorrow we will, I think, not me, tomorrow's lecture will be handled by another faculty from Dumitra. So you will get answer for that tomorrow. My opinion, if you ask, it is not yet detected, but the evidences say that, or the other observations say that it should be there. Okay. So it may be, yeah. No. Devansh. Devansh.
Sir, I wanted to ask you what is a wormhole?
Wormholes and all these things are actually kind of theoretical things. There is nothing real about it. So wormholes are considered to be the warping in space-time, so that a different part of the universe is connected through a tunnel-like thing. So it is something like a paper curved together so that it is connected from one side to there. So there are some theoretical things, but not yet it has any evidences.
Okay, sir.
Yeah. Any more questions? Something in the chat. So what happens when two black holes hit each other? So when two black holes hit each other, it forms another big black hole, along with the emission of high energy X-rays and gamma rays, and which is actually known as the gamma ray burst. Okay, and the same thing will happen when two neutron star merge together. Again, when two neutron star merge together, it will form not form another neutron star. Instead of it, it will make another black hole. Okay, and during which also there will be the emission of high energy gamma ray. This is called gamma ray burst. Okay, GRBs, they are known as GRBs. Okay, so that's about it. I think there is one more hand raised. Just a second. Yeah, Anushka. Yeah.
Sir, what is the difference between pulsar, variable star, and Cepheid?
So pulsars are basically what is called the neutron stars. Okay. So it is not a normal star. We can call it, even though we call it as a neutron star, it is actually the end stage of a star, which is completely made of neutron, and there is no nuclear reaction is happening there. And it is highly magnetic. It emits radiation through its two poles, and it is finally, because of it rotating, when something is rotating and light is coming out of it, when it is pointing towards you, you can see. When it is pointing away from you, you cannot see. So it repeats actually. So it is something like a lighthouse. So we get a feeling of pulsation. So that is called a pulsar. Okay. So pulsar is entirely different from variable stars or Cepheid variables. So variable stars are actually the general class of Cepheids or any kind of stars which vary its brightness. Okay, they are generally called as variable stars, and particularly the one which has this certain property that it vary its brightness regularly. Anyway, Cepheid variables also comes inside the variable star, but the Cepheid variable has this specialty that it brightness varies, of course, because it's a variable star, but its period, okay, its period of that pulsation or the brightness variation depends on its luminosity. So they are called the Cepheid variables.
So can
So,
we put variable stars on the HR diagram?
of course, no problem, we can put it.
But
But there will be some variation in its luminosity, so it won't be a certain place, but those variations are not that huge variation. So in this scale, actually, it won't change much. But anyway, at a particular point of measurements, we can put it in the slide. No, put it there, no problem.
so can you explain pulsars again? I didn't understand.
A pulsar is basically a neutron star. Okay, just imagine a neutron star which is made up of completely neutrons. Anyway, that is a spherical object, so small. Now just see that. So or just leave. You have a ball in your hand. Okay, and from the ball, there is some light is coming at two ends, diameter, two opposite ends. Some light is coming outward. Okay, imagine. Now this ball is rotating. Okay, when this ball rotates, the light is actually coming to you, but during this rotation, the light, sometimes it comes towards you, sometimes it's go away from you because of the rotation. So just see here, this is the neutron star, and assume that some light is coming in this direction. Okay, you can see light is come this direction. Now you are standing here, so far away, you are standing here with a telescope panel, and you can see this star. Okay, and now what will happen? Now assume that it is rotating in this direction. So what will happen? After some time, this light ray coming to you will move in this direction, and this will move in this direction. So you cannot see. So now what will happen? It will rotate, and this side will come to your side. So you can see this pulse. Then at that time, the pulse that you are seeing will come here. Then again it will come here. Again it will come here. So because of that, there will be a pulsation. It is not the variation, it is pulsation, on and off. Okay. But in the case of variable star, it is not turning on and off. This feels like a turning on and off. Okay. So this is called a pulsar.
Understood, sir. Thank you.
Okay. Bhargav Deshmukh.
Sir, is it possible to have a naked singularity?
I'm not sure about that. You can ask those questions tomorrow, I think. It is there are many things. He may be much more better to answer those questions regarding this because it comes in general relativity and all. So
Okay.
you can ask it tomorrow. Yeah.
Yeah, thank you.
Sauja's MG.
Sir, you mentioned about neutron stars, no, sir?
Yeah.
So what actually happens to the neutron star after like does it die or what happens to it?
It may lose its energy, that's all. Anyway, it will stay like that, that's all.
Like it'll stay like that forever or like how, sir? Like
Yeah, it stay like that forever. Something like a white dwarf.
okay, sir.
Yeah. So I hope there is no questions remaining. We can wait. No problem. It is, yeah, 3 more minutes we can wait. Yes, Sri Mahitraj. Yes.
Sir, then eventually all the stars will become as a black hole or a white dwarf, sir.
Eventually, all the stars actually, stars will die for sure. It may become black hole, may become neutron star, and at the same time, some of the low mass star becomes planetary nebula. But even when this is happening, it is ejecting so much material to the space back. Okay, so all the material it accreted will not become black hole or neutron star. So it will emit back most of the material back into the space itself. So again, from those masses or from that ejected material, another generation of stars can form. Okay, so it is a cyclic process.
Okay.
Yeah, Krisha Desai.
Sir, which generation of star is our sun?
It's a second generation star.
How do we know that?
We are saying it based on I'm just muting for I can hear back your echo actually. Yes, thank you. So so the sun is said to be a second generation star because the first generation stars are the stars that formed just after the Big Bang. So from that Big Bang, there are material ejected out. Okay, so not from the Big Bang, from the first generation stars, there are many materials ejected out through the universe, okay, to the space. And that is why then only if the sun was a first generation star, then there will be around the sun, there won't be any other materials like the maybe something like the oxygen, carbon, or magnesium. Any other element won't be found. These elements to have those elements, the sun should be the next generation star or the second generation star. Why? Otherwise, the problem is that we couldn't get the materials that is needed for life or the Earth from a first generation star, if sun was a first generation star. So since we are the second generation star, that is why we have all these materials around us. So I hope now, what is the time? Yeah, it is 9. Almost all the doubts are over. So once again, thank you so much for being with me for the past 4 days. And tomorrow, another faculty will join with you. And all the best for your exams, and all the best. Thank you. Thank you so much.